Okay, good morning. So in the last lecture we started talking about monads, and we introduced the so-called I/O monad, the monad for doing input and output. Now the general idea of the I/O monad and of monads in general is that they encapsulate a certain value. So what monads do is monads are a special data structure, or special kinds of data structures which encapsulate values. So they encapsulate values. For example, if you have an object of the data type IOA, then in this object, an object of type A is encapsulated. It's inside this object, but it's difficult to get it out of this object again. You can access this encapsulated object by certain predefined functions, but you cannot just take it out. So for example, here, an object of type A is encapsulated in the object of the type IOA, and you can only access this object with certain predefined operations, but you cannot just take it out. Access to the A object is only done via certain predefined operations. Predefined. Let's via certain operations. For example, via this bind operation. You cannot just take it out. Now, we had some predefined operations on the I/O monad in the last lecture. The easiest one is put character. So put character creates a new I/O monad object, and the objects of this particular monad type are actions which perform input or output. And the special type I/O empty tuple represents output actions. So put character is a function which takes a character as an input and gives you back an action, an object of type I/O empty tuple, and this action happens to print this character on the screen. You can compose actions, or in general monad objects, by this double greater. And what happens is, well, you take two actions, you perform them after each other, and that's it. That's the resulting action. And the object which is encapsulated in the first action is completely ignored. So if this is the first action, here you do this action IO1, and during this action, this value is determined, computed, encapsulated, and then afterwards you do this, but this value A is completely ignored, so the result of composing them with double greater is simply this action. Now there is a better way of composing monad objects or I/O actions, namely this bind operator. This was called then, and this is called bind. And here you first perform the action in the first argument, and then the second action depends on the value that was encapsulated in the first action. So you first perform this IO1 action. During this action, a value A is determined or encapsulated. And then the second action, IO2, might depend on this value A of type A, which was determined here. So depending on this value A, different actions might be performed, and during these actions, a value of type B is determined. So you can depict it like this. Now, some other predefined operations. We had an operation called getCharacter. And this operation getCharacter creates a new object of type IO character. And the character which is encapsulated here is the character that the user types on the keyboard. So getCharacter waits for the user to type something on the keyboard. And so the whole thing that it produces is an IO action where you wait for input from the keyboard, a character from the keyboard. And then we also had return. Return creates an empty action. So return takes a value and gives you back the object where this value is encapsulated. And in the particular case of the I/O monad, no particular action is happening. So there is no input-output taking place, but the result is the empty I/O action with the A object encapsulated. So here are two examples. If you write this, then the result is an action which first reads a character, but since we have then and not bind, the value of this character is ignored, and then you do the empty action where you encapsulate the empty tuple, and that's the sign for an output action. So this is the empty action. First read a character and then do nothing. And this means first read a character and then print it on the screen. More formally, put character is not an I/O action on itself, but it's a function. It waits for a character and then it gives you back an output action. The output action which prints this character on the screen. So it takes this character out of the encapsulated I/O object over here and prints it on the screen. So this was what we did in the last lecture. And then we wrote an algorithm to illustrate how to work with monads and with I/O monads in particular. We wrote the following algorithm which reads a number of characters, not just one character, but many characters from the screen. This function gets. Now this we had at the end of the last lecture. So how does this work? Gets takes an integer, a number, and then it reads, so if the number is, say, n, then we will read n characters from the screen, and that's what's happening. So what's happening is the result is an I/O action which reads a string from the keyboard, a string of this length, and this string is then encapsulated in this I/O action. So how would it work? If we want to read 0 characters, then the output, the result should be an empty I/O action. That's the reason why we use return here. And what is the value that was determined here? What should be the value that is encapsulated in this I/O action? It should be the empty string, because we read a string of 0 characters. And if we want to read n plus 1 characters, then how can we do it? Well, the first action that we want to perform is we want to perform the action get character. So get character is an I/O action in which a character is encapsulated. Now, to take out this character out of this I/O object, we need this bind operation. This bind operation is the only operation with which we can ever access the object that is encapsulated here. So in order to get this A out of the I/O object, we need the bind operation, because the bind operation, after the bind operation, we have this whole thing is a new I/O action of type I/O string, but it depends on the value that was encapsulated here. So we take the character that was read here, the x, and then depending on the x here, we do another I/O string action. And what does this I/O string action do? Well, it calls gets recursively, so it reads the remaining n characters from the keyboard. And so here we have an I/O action where the string of the remaining n characters is encapsulated. And to get this string out, we again use this bind operation. And so this thing here, this return thing over here is again an action of type I/O string, but it depends on the values that were read before. So we take out the string that was read here, this is this axis, and we take out the x that was read in the first step, and we put them all together, and this is the final result. So we do 3 actions. First, read the first character, then read the remaining n characters, and then do nothing. So 3 actions take place. And what we encapsulate in the resulting action, which composes these 3 things, is this, x colon x's. So we encapsulate the string which consists of the first character and the string consisting of the remaining characters. Now, as I said, this is pretty unreadable, and there's a much nicer notation for this, because this is a typical form of working with monads. Since the only way to access this object that is encapsulated here is via this bind operation, this is the usual way how programs with monads look like. And since this looks very ugly and hard to read, there's a special notation called do notation. So there's a do notation to ease readability of programs that use monads. And this is just syntactic sugar. So this is just a different notation for the stuff you read over here. So instead of something like this. So first you do an action P of type IOA. So this is an IO action, and during this IO action, a value of type A is determined or encapsulated. Then we want to access this encapsulated object of type A. So after this, there should be an action which depends on this encapsulated object X, and depending on X, we do another action Q. So X has type A, and Q has type IOB. So this expression performs two actions after each other. First action P, and then action Q, but how action Q looks like depends on the value that was encapsulated here. Because we take this value out, this X, and this X can occur in this Q, and depending on the value that was encapsulated here, different things can happen there. Now you can see this is also the form that we used over here. So whenever you use bind, then typically your programs will look like this. And in order to avoid this, one can write the following. We write do, and now we simply write this. So what does this mean? So this do opens up a new block of declarations. So if you like, you can also write this with curly brackets and with semicolon, but you can also use this offside rule, which says that if you write things below each other, then they belong to the same recursive block. And now what this says is, you can read this like an imperative program. X is the value of P, and then afterwards you do Q. So this looks like an imperative program where you have assignments. So X is assigned the value of P, and then afterwards you do Q. Maybe another longer example to make it even clearer. So instead of writing this, so this is, here we had an expression with just one bind operation. Here we have an expression with two bind operations. So this looks like the algorithm over there. First perform action P, then keep the value in mind that was computed in P, call it X. Afterwards perform action Q. The value that was computed in Q is called Y. And then afterwards perform action R. So do these three actions, P, Q, and R, but keep the values that were computed during P and during Q in mind. And this value that was computed during P, we call it X, and the value that was computed during Q, we call Y. Now instead of this, you can also write that. Do the following thing. So do opens up this special form of declarations. First let X be the value of P, then let Y be the value of Q, and then do R. So this reads like an imperative program. You perform several statements after each other from the top to the bottom, and here we have a variable. The variable X should get the value of P, and so on. So if you think of Java, you would write X equals P, semicolon, Y equals Q, semicolon, R. Now, this looks like imperative programming, but it is not imperative programming. In reality, this is just a shorthand for this, and that is not imperative at all. That's purely functional. It simply looks like this. But it makes things much more readable. So, in general, this do notation can be defined as follows. Or maybe I first show you let's first look at the example. So let's rewrite this gets definition, but now we use the do notation. And now you will see that this becomes very readable. Now, if you write it in this do notation, it looks like this. Okay, first case is the same, but in the second one we change something. So if you want to read n plus 1 characters from the keyboard, what do? You perform these actions after each other. Do. First, you perform action get character, and the value that was computed here, you bind it to the variable X. Then you perform the action gets n, and the value that was computed here, you bind it to the variable X's. So this is the first character, and this is the string of the remaining n characters. And then you return the result, and the result is X:X's. Now this looks as I said, like in imperative programming, and that is quite readable. I mean, this is exactly how you would do it. And this is just a shorthand for this. So internally, Haskell expands this to that. So this is what is really happening. But of course, if you want to read your programs, this is much easier to understand. So do is just an abbreviation. So the definition of do is therefore as follows. If you write do and then x arrow p and then some remaining declarations, let's call them s, then this is the same as writing you first perform action p and then you bind the value that is the result of p to the variable x, and then afterwards you perform this remaining block s. I'll write this s inside here. So this is another sequence of such expressions where you either have variable arrow action or an action on its own. So this is the first case of the definition. The second case of the definition is what happens if you write just do. Here you have an action, and there you have another block of actions or variable arrow action. This is a shorthand for the following. Now you first perform this action, but you ignore the result that was computed here. So now you compose this action with the remaining stuff, not via bind, but via then. So this is it. And then you do with the remaining stuff. And then finally, if you just write do p and this stuff is empty, this is the same as p. So this is the meaning of this do notation. And if you don't like it, you don't have to use it, since you can express it via bind and then. But of course, it makes programs much more readable. So what is the main advantage of doing input-output in this way? So what are the advantages of doing input-output via monads? Of input-output with monads? Well, the big advantage is that you have a clear separation between parts of the program that have side effects, so parts of the program that really does input and output, and those parts of the program that have nothing to do with input and output. So there's a clear separation between I/O parts of the program and between the rest. And the rest of the program is the part that has no side effects. So the rest is the part without side effects. So what I mean by that is you have those things that are influenced by the outside world. For example, when you read a character from the keyboard, those parts are encapsulated in these I/O objects, and they can never come out of these I/O objects again. So values which depend on the outside world. So for example, a character that the user types on the keyboard. That's something that does not depend on the program on its own, but it depends on the outside world. And this value, you can never get out of this I/O monad again. This is in this I/O monad, and you can put it into another I/O monad, but you can never get it out. And therefore, it can never influence the value of expressions. So values which depend on the outside world are encapsulated in IOA objects, and they can never be taken out of such objects. So you can never, I'll show you in a moment. They can never be taken out of such objects. So in other words, the values of Haskell expressions are always the same. They never depend on the outside world. So in other words, we still have referential transparency. So what I mean by this is you cannot write a function which reads a character from the keyboard and then returns this character as its result. So that's something that's not there. So there's no function of the form result of type IO character, which would, or in general IOA goes to A, which would give the encapsulated value of an IOA object as its result. So you can't write a function which first performs the action, read a character from the keyboard, and then gives back this character as its result. You can write a function which gives back an action where this character is encapsulated, or which gives back an action where a modified version of this character is encapsulated. But you have no possibility to get this character out of an I/O action again. You can put this character into another I/O action. You can put a modification of this character into another I/O action, but you can't get it out. It is in this I/O action, and this makes sure that those parts that are influenced by side effects, they are clearly separated from the rest of the program. The rest of the program operates with data objects which are not in this I/O, which are not encapsulated inside this I/O monad. But inside this I/O monad, this is the only place where you have things that depend on the outside world. And now this is the reason why it is nice to have input-output with monads. In general, you can also use monads for other things, not just for input and output. But monads can also be useful for other purposes than I/O, and the user can write monads himself. And this is what I will discuss next. So the last section of the practical part about Haskell is now how to use monads in general and how to write your own monads and why this can be good. So this I/O monad is obviously predefined, and if you want to do input-output, then you should use it, and it has the advantage that side effects are clearly separated from the rest of the program. But you can write other monads yourself, and I will try to illustrate why this can be useful. So now we come to general programming with monads. And now, as I promised, now I will tell you what monads really are. I mean, we have just seen one single example of a monad, namely this I/O. But what monads really are, I didn't really tell you. And monads are, a class for monads is predefined in Haskell. So monads are predefined in Haskell as follows. So monads are defined via a class. So it is a class monad So you remember what class means? We introduced class for type classes. So we said M is a member. If M is a type, then this type is a member of the class monad if it has the following operations. And now there come several operations that should be present in every instance of this class. Now, if M is a monad, then there should be at least the operations return and bind. So these operations that we know for the I/O monad, they should be present for every monad. So this is something that is characteristic for every monad. So what would be the type of return? Return takes an object of any type A and gives back a monad object, MA, where this object is encapsulated. And bind is used to compose two monad objects. So it takes one monad object, MA. So if you replace M by I/O, then these are the same types that we had before. Up to now, return took an object, A, and encapsulated it into IOA. Now, instead of I/O, I write M, and that's the only difference. So if I put on this slide, you can see that these types are exactly the same that we had before, but instead of I/O, I write M now. So in general, bind is an operation which takes one monad object and another monad object, where an object of type B is encapsulated. But this second object might depend on this first encapsulated value. So the second is a function A to MB. So it's a monad object of type MB, which, however, depends on A, on this value that was encapsulated here. And the result is the composition of these two objects. And there are some more operations. For example, then is also present, and so on. So when you look at this closely, you can see that monad is not a type class. So monad is not a type class as we had it before, because this M here is not a type. MA is a type. So M is a type constructor. It's a type constructor of arity 1. So M is like the list type constructor, the square brackets. So M waits for a type A, and then MA is a new type. So this is not a class of types, but a class of type constructors. You can do something like this in Haskell as well. So monad is not a type class, but a constructor class. But a constructor class. So in other words, this M up here is not a type, but MA is a type. And so M is a type constructor with arity 1. So M is a unary type constructor. And for example, an instance of this class is I/O. So again, the following declaration is predefined, which says that this type constructor I/O, which is a unary type constructor, so I/O character is a type, I/O int is a type. I/O waits for a type and gives you a new type back. So I/O is an instance of this class, and now here we would define how return is actually defined. This is somewhere in the prelude of Haskell. It is defined how return is actually implemented for this type constructor I/O. and how bind is implemented and how then is implemented and so on. So this is again predefined. Now, so what this means is certain type constructors belong to the class monad, and if these type constructors belong to the class monad, then we must have functions like return and bind and then and so on. So this is how monads are defined in Haskell. Now, as I said, the concept of monads comes from category theory, and in order to really call this a monad, I mean, you can, of course, implement return and bind and then in any way you like. Now, in mathematics, if you implement this completely arbitrarily, then you wouldn't call this a monad. So in order to be really a monad, you should implement them in such a way that they satisfy certain properties. So in Haskell, every unary type constructor that implements things like return, bind, and so on can be an instance of the type class monad, but you should not do this. You should not implement them completely arbitrarily, but you should make sure that return really is some kind of an empty statement. So return really should only take an object and encapsulate it in this monad. And bind should also not do something completely arbitrarily, but bind really should combine or compose two monad objects. But one should not do it, but these implementations should, so Haskell will not check this, but as a programmer you should check it. These implementations should satisfy the following three monad laws. So these laws say what return and bind should do. And in reality, only if this is satisfied, you would call it a monad. Now, Haskell does not check it. You can still call it a monad, even if your return implementation and your bind implementation does something completely strange. But you should try to satisfy these three laws. So the three laws simply say return does nothing, and bind combines monad objects. This is what is expressed here. So more formally, the first law says if you take a monad object, P, and you combine it with return, then you should get P again. So return is the right neutral element of bind. So in other words, return is a right neutral with respect to bind. So what does this mean? This means if you have an object of type MA, so this is a monad object where an object of type A is encapsulated, and then you combine it with return, and return does the following thing. Return takes an object, A, and gives you back a monad object where this is encapsulated. Then what should happen is you just get this. So when you do this empty thing afterwards, this empty encapsulation function, nothing should change. You should get P again. So this has type MA. Now in the special case of the I/O monad, this means if you do this action and then afterwards you do the empty action, then this is the same as if you only do the first action. So this makes sure that return really does the empty action if you do first something and then return. Now it should also work the other way around. If you first do return and then you do P, then again this should be the same as just doing P. So return should also be left neutral. This is the second monad law. So if you first do return, and what do you return? Well, you return anything. So this is an object of type MA. And then afterwards, you do something else. So you do some f. And f is a function which takes this a and then does something else, some mb, so some monad object where b is encapsulated. Then this should be the same as immediately doing fx. So this thing is of type mb. So basically this means if you combine a return object with another monad object, you get this other monad object. The only thing that happens is you take this encapsulated x out of this first monad object. So return is left neutral. Neutral with respect to bind. And the last monad law says that bind is associative. It doesn't matter whether you first, if you have three actions or three monad objects, P, Q, and R, it doesn't matter whether you combine P and Q together and then perform R, or whether you first perform P and then combine Q and R together. So it's associativity of bind. That's the last monad law, but to write it down, I need another board. And don't be shocked, afterwards I do a very illustrative example where we program something again, which is not too hard to understand it, but it does not influence the rest of the lecture. So afterwards, I will look at other features of functional programming again, which don't use monads. So you will understand the rest of the lecture, even if you don't understand monads. Okay, so monads are type constructors where you have operations like return and bind. And the implementations of return and bind should satisfy certain properties. And the first two, there are three properties they should satisfy. Property 1 and 2 say basically return does nothing. So if you compose a monad object with an object that you created by return, then you get the first object again. And it doesn't matter whether you do this the one way, in the one order, or in the other order. And the last monad law number 3, is the associativity of bind. So what does it mean? Let me first write it down without brackets. So if you first do P, P is a monad object of type MA. Now then afterwards, you bind this, you take the X out, and you do Q. So X is this object that was encapsulated here, A, and Q then is an object of type MB. And now you bind this again, and you take the object out that was computed during Q, let's call it Y, so this is of type B, and then you do R. So this has the type MC. And now the question is, how do you execute this? Do you first perform this bind or this bind? This bind, if you perform this bind first, then you first compose these objects P and Q, and then afterwards you compose it with R. And if you execute this bind first, well, you first combine Q and R, and then, well, you first perform P, but then you do the combination of Q and R. And this law says it doesn't matter where you put the brackets. So whether you put the brackets here or whether you put them there is the same. So I write it down again, same statement, but now I put the brackets differently. So this is the same statement as before. The only difference is that now I put the brackets around here. And this is the same. So in other words, bind is associative. Of course, to make this more readable, you can also write it down with the do notation. So this thing basically means, let me first write this. So this means, what do we do here? Well, we compose two things. One thing is the thing in brackets, and the other thing is this over here. So what we do here is the outermost bind is this one. So this is on the topmost level. So what happens is y is bound to the result of this bracket expression. So y is the result of this bracket thing, and then afterwards we do r. Now what is this bracket thing? Let's translate this into do notation as well. So what happens here is, first x is bound to the result of p, and then we execute q. So x is bound to the result of p, and then we execute q. So this expression is the same as the stuff that is written up there. And what we did here is we group p and q together, and then afterwards we do r. And this is the same as, this should be the same as this. And here we really execute it the other way around. So here we first bind x to the value of p, and then we execute the rest. So then afterwards, we do the following thing. We bind y to the value of q, and then we do r. So instead of having to write such a nested form of do's, you can put this all on top level. And that's something that should be satisfied for monads. And if you program monads yourself, then it's your duty to make sure that your implementation of return and bind satisfies these properties. Now, the implementation of the I/O monad satisfies this, and whether your own monad satisfies this, that depends on you. Now, what are monads good for? Oh, by the way, this do notation is the do notation you can also use for your own monads. So this can be used for all monads, also for user-defined ones. So as soon as you define a type constructor yourself and you say this is an instance of the type of the constructor class monad, then if you do this, you can also use this do notation for your own monad. So whenever you have a monad, Haskell allows you to use do notation. Okay, now an example which should hopefully convince you that monads are a good thing and that you should write monads yourself. And now this example has nothing to do with I/O, because why monads can be good for I/O I already showed you, but monads can be good for other things. And the big advantage of monads in programming, of monads except for I/O, or in addition to I/O, is that you can write programs which are particular modular and particular easy to maintain and to modify. You have better modularity of programs, and you get programs which are especially easy to modify and to maintain. And I will try to illustrate this with an example. Okay, so the example with which I want to illustrate this is we want to program something like a pocket calculator. So basically you want to evaluate terms. Terms with arithmetic expressions like division or probably subtraction and multiplication and addition, and they should be evaluated. So the example is we want to program an evaluator for terms, and these are arithmetic terms. So. And we will first do this without monads, and I will first program a simple version of this evaluator, and then we will see how this simple version could be improved. Then I will improve it, and you can see that we have to rewrite the whole program. And then with every new improvement, I again have to rewrite this whole program. So whenever we want to change a little bit, this means rewriting the whole program. And then I will do the same thing with monads again, and then you see that the changes are very minor. Whenever we want to improve something, we have one small change at one particular position, and that's it. So so without monads, stepwise improvement of the program requires many changes, and with monads, a stepwise improvement requires only very few changes at certain points which can be identified clearly. Okay, so our example. What we want to do is we want to evaluate terms, as I said, and to evaluate these arithmetic terms, we define a data structure of arithmetic terms, which should then be evaluated. This data structure will look like this. We say term is a new data structure, a new data type. It has two data constructors, one for constants, con, and one for arithmetic terms which are built with division. Now, to make this example short, this will be the only arithmetic operation that we will look at. Of course, in reality, you would like to have something like add and mult and subtract and whatever. You want to write down terms which represent arithmetic expressions. So con should take is a constructor which takes a floating point number and gives you back a term. This represents that particular number. And diff takes two terms and gives you back a term. And this represents the arithmetic expression which corresponds to dividing the first argument by the second. So something like con 6, this term stands for the number 6. And if you write something like diff con 6 con 3, this stands for the arithmetic expression 6 divided by 3. So with this data structure, you can represent arithmetic expressions where, in fact, the only arithmetic operation that I have here is division, but this is just to keep the example short. In reality, you might like to have something like plus and times and minus and so on. Okay. Maybe another. Let me call this term T1. And I want another term T2. Of course, you can also write something like this. Diff of con 1, con 0. And this stands for the arithmetic expression 1 divided by 0. Now, of course, this is somehow a problematic arithmetic expression because division by 0 is not allowed, but we will come back to that later. Okay, and what we want to do is we want to evaluate such terms. So we want to write something like a pocket calculator, so a function which takes such a term and evaluates it. So a term like this, diff con 6 con 3, should be evaluated to something which represents the number 2, because 6 divided by 3 is 2. How can we do this? Now, version 1. Now we do program development, and the first implementation of this evaluator is very straightforward, and we don't use monads. So we do everything without monads, and then we see what the disadvantage is, and then we do it again with monads. So we first do simple evaluation without monads. So simple evaluation without monads. So our goal is to write an evaluator, a function eval, which takes a term and gives you back an object which can then be printed on the screen. So our goal is write a function eval. I call it eval1 because this is the simple evaluation, and when we approve it, we will call the next version eval2. Function eval1 takes a term and returns an object of a type which can be printed on the screen. So, in other words, we want to return an object of a type where the type is a member of the type class show. So there should be a show function defined because show converts objects into strings, and whenever you evaluate something in your interpreter, then afterwards the result will be depicted in your interpreter, and what will happen is the function show is called to convert this object into a string. So the result type should be a member of the type class show. Okay, and one possibility to do this is the following. We use the following data type. I call it value. We use the following data type value. So value is a new value A is a new data type. Value is a type constructor. So whenever A is a type, then value A is also a type. And the only data constructor of this type is called result. And now to make this an instance of the type class show, we have to declare this. So what we can say is the type value A should be an instance of this type class show. So in other words, every object of type value A can be depicted on the screen, provided that A is also a member of the type class show. So if there's a show function with small s, which can convert A objects to strings, then there should also be a function which converts value A objects into strings. And we can implement show ourselves. We can say, well, an object of this data type has the form result x. So result is the data constructor, x is the value, which is the object of this data constructor. And to print it on the screen, well, we give back this string. So the string, which first consists of the word result, and then the string for x. So here we call show the show function for this value x. So if we do this, then what would happen? So for example, if we, with the implementation of show for the data type value A, if we, for example, have an object like result 6. Now this is an object of data type, this is data type value int, for example. If we have this object, then how would it be depicted on the screen? Well, to depict it on the screen, the function show would be called for this data object. And this would be printed as the following string. The string which first has the word result, then a colon, then a space, and then 6 would be converted into a string, so it would look like this. And now, how can we define this eval function? Now, eval should do the following thing. Eval1 should now take a term and give us back an object of this value data type. So it should be an object of type value float. So a term would be converted into an object of this type, which can then be printed on the screen. And how would this evaluator look like? That's rather straightforward. it would look like this. So how can we convert terms into value objects? A term which represents a constant, so con x, would be converted into this object, result x. So con is replaced by result, that's all. And now if we then print it on the screen, we would have result, colon, and then the value that was of this constant. And now if we have a term which is built with diff, then we would first evaluate the first argument, so diff tu. We would first evaluate t, and the outcome would be some value object, result x. And then we would evaluate u, and the output would be something like this, result y. Then we take out, and then we compute x divided by y, and the final result of this function would be result with x divided by y. Now this simply converts terms into value objects, and it actually performs these divisions. So let's look at an example. So if T1 is this term. So if I call eval1 T1, then what will happen? Well, first this thing, con6, will be evaluated. This gives us result 6. Then con3 will be evaluated. This gives us result 3. Then 6 will be divided by 3, which gives us 2. And then we get back the result of 6 divided by 3. So in other words, we get back result 2. So on the screen, we will see result colon 2.0. 2.0 because this is a float. But what would happen if we do eval1 of T2? Okay, now it would first evaluate con1 and con0, which gives us result 1 and result 0. And then it would try to divide 1 by 0, and then we would get a program error because you cannot divide by 0. So this gives us an error because of division by 0. So, I mean, we try to develop a program. So the programmer has developed eval1 and says, great. And then he gives this program to the test division, and the test division starts testing. And indeed, if you evaluate T1, this works perfectly. But if you evaluate T2, then the program breaks down. And so he gives it back to the program developer and says, look, I have found an example where this behaves strangely. Repair this program, improve it, such that it behaves sensibly for such inputs as well. And now the programmer has to rewrite his program and try to improve it to capture these cases as well. Of course, this is a small toy example, but this is just meant to show you how program development would work and how monads would improve it. So now the program developer says, okay, I forgot to think about division by 0, so I will now modify my program to make sure that divisions by 0 don't occur. And you will see that to do this, he has to change lots in his program. Okay, so version 2. Instead of simple evaluation, now we do evaluation, but we also take these exceptions into account. So we do this kind of exception handling. So evaluation with exception handling, maybe this would be. So evaluation with exception handling, but again, without monads. Okay, so the programmer says, okay, I forgot about division by 0. Let's throw this program away. Let's do it again. So maybe this value data type was not so good, because with this value data type, I can only represent results. So I mean, this is there to represent numbers. But how do I represent an error? And so he comes up with a new data type, which is called maybe. So maybe looks like the value data type, but instead of just one data constructor, now we have two. So maybe is like value. So what was called result before is now called just. So Before, result was simply meant to take an object and put a data constructor before it, encapsulate this object, basically. It was called result before, now we call it just. But there is another constructor, data constructor, nothing, which represents exceptions or mistakes. Nothing to represent exceptions. Now, by the way, this data type is predefined in Haskell because it is pretty useful. But anyway, we define it ourselves now. Okay, so what did we have? Now we have changed the data type. Instead of value, we use maybe. Now, of course, we also have to change the show function. Show says how to depict objects of this data type on the screen. So, okay, we also have to write the show function anew. And now how would it look like? We say that the data type maybe A should be a member of the type class show. So in other words, objects of type maybe A can be converted into strings, provided that objects of type A can also be converted into strings. So an object just X, we would convert into the string where you first have the word just and then the string which corresponds to X. And if you have the object nothing, we convert it into the string nothing. So this is the way we modify this show function. And now we have to program the evaluator again. Now that leads to function eval2, which looks like this. Okay, how does it work? Now, our goal is we want to evaluate terms again, but the result is not of type value float, but of type maybe float. Now, terms which represent numbers are converted into objects of this maybe data type, but here we have just. So the only difference is whenever it's a proper number, we write just, and whenever it's a program error, we write nothing. Now, this is a number, so it's not a program error, we write just. If we want to convert the term division of t and u, then we first evaluate t. Now, there are two possibilities. Either the evaluation of t leads to an error, because somewhere in the evaluation of t, we would have to divide by 0. In this case, t would be evaluated to the value nothing. Otherwise, it would be evaluated to a value of this form, just x. Now, if t is nothing, so if evaluation of t leads to an error, then evaluation of this thing should also lead to an error. So we should immediately return nothing before evaluating u and before trying to divide something, dividing the value of t by the value of u. If evaluation of t works properly, then we evaluate u. Now again, evaluating u might lead to a program error because to evaluate u, maybe we have to divide by 0. In this case, we would get nothing here, and we should return nothing. And if evaluation of u also works fine, then we should now divide x by y. However, we should not do it if y is 0. So now we test whether y is 0, and if it is, then we should not evaluate anything but return nothing. And if it's not 0, we should return the object just x divided by y. So now we would get x divided by y, but with a just before. Now, what is the difference to the old implementation? Okay, what was called just is now, what was called result is now called just. That's not a big difference. So here in this line, we have no big difference. But here we have a lot of differences. The only difference which should really be there is this one. Because, I mean, somehow we have to tell the program that if the divisor is 0, then that should be a program error. Now, this part is really necessary. This change we need. But these remaining changes, they say, if one argument already led to an error, then the whole thing should lead to an error. This stuff is a lot of new things that we have to program. And we don't only have to add this for div. Imagine that we also have terms with plus, with minus, and so on. Now, all the implementations for plus, for minus, and so on, we have to add things like this, saying, well, if one of the arguments leads to an error, then the whole thing should lead to an error. So all this stuff we would have to add in each of these defining equations. Now this becomes completely unreadable, and you have a lot of modifications which are all similar, but you have to do them all. So what we can see is this modification requires a lot of changes. And in particular, it requires a lot of changes in the evil function. And this would be even worse if we also had terms built with, say, plus, so further data constructors in addition to diff. If we also would have plus or minus or mult or times and so on. All these changes you would have to do in every defining equation, and you do the same thing over and over again. So a small change, I mean, the idea of the change between this version and the previous one is not so big. The only difference should be if we divide by 0, this should be a mistake. But this small change, this conceptually small change, leads to many, many modifications in the program code. Now, that's not very nice. And of course, you can then think of further improvements. So if you look into the course notes, this example is much longer. So in the course notes, I made 2 more improvements. Another improvement where suddenly you come up with the idea you also want to count the number of evaluation steps. And this is also something that the evaluator should do and then depict on the screen, and so on. So you can make many, many more changes. And with every change, you have to rewrite your program completely. And if you use monads, this can be done much easier. So now I write this program again, but now I use monads. So now I do 1 prime. 1 prime is again the simple evaluator, but this time with monads. Now, let's go back to this simple evaluator. So this was version 2. Here we have version 1. This value is a type constructor of arity 1. This value, in fact, should be a monad. Value. And this monad has a special name. It's called the identity monad because this value does nothing else than encapsulating objects inside a data constructor. It's the so-called identity monad. So we should declare value as an instance of the class monad. How do we do this? So we define value as before. I mean, value A is the new data type. The only constructor is result. But we say that value should also be an instance of the class monad. So value is an instance of the class monad. And now, of course, we have to say what return is and what bind is. Now, what should return be? What is return? What is bind? Now, return, what's the meaning of return? Return should take an object and give you back a monad object where this value is encapsulated. So in other words, return has, in this case, the type, we take an object and we give you back an object where this, we give you back an object of type value A where this A object is encapsulated. Now, how can you encapsulate objects of type A into value objects? Simply by writing a result in front of it. So return is simply result. So return of x gives you the object result x, and that's the value object where simply the argument of return is encapsulated. Now, what is bind? So bind should do the following thing. It takes one object of type value A and then binds it to another value object Q. Now this Q should have the type A goes to value B. So 2 value objects are composed. first this thing and then this thing, but this Q object depends on the value A on this X that was encapsulated here. Okay, so this Q is a function. What it should do is it should be applied to this X and then give you back this value B. So how to define it is the following way. It should simply be take this function and apply it to the encapsulated value. That's the idea. We want to make sure that bind really extracts this encapsulated object here and then puts it into this value over here. Now if we define this, if we say value is an instance of the class monad and return and bind mean this, then we can rewrite this definition of evil in a different way using return and bind, or to make it more readable, using do. Now, even for our own data type value, we can now use do notation because now value has been declared as an instance of the class monad. Okay, so this is what we had up to now. And now how would this look like? If we use the do notation, it would look like this. Now maybe it would be nice to see these two things together. Okay, I first explain this and then now we should watch it together. It will be difficult to have this on one slide, but it will work. Okay, so on the top I have this. So this is our old implementation without monads. And up there we have the new implementation with monads. They do the same thing. You can write it both like this and you can write it like this. But this way of writing it exploits that we know now that value is a monad. Okay, up to now we have said that when we want to evaluate a constant expression, what we give back is this object built with this data constructor result where this object is encapsulated in. Now, instead of writing it like this, we can also write return x, because return, in the special case of the monad, of the value monad, return is the same as result. So this is obviously the same. And what it actually means is return this object where x is encapsulated. And how this encapsulation actually works, that is defined in this instance declaration. And now in the case of div, up to now what we did was we first evaluated t, and then we got an object here, and we evaluated u, and we got an object here. And then we took out this x and this y from these objects, we divided them by each other, and then put it back into a value object. Now this is the same thing that is written here. First evaluate t, and the object that is encapsulated in the resulting monad object is x. Then evaluate u, and y is the thing that is encapsulated then. And then give back another monad object, but the thing that is encapsulated here is x divided by y. So these things are really identical. They do the same thing if you implement return and bind in this way. Now, if you forget about monads and you just read it like an imperative program, it's very readable. It means, okay, what do you return? For a term which is simply a constant x, you return x. If you want to evaluate this term, what do? You evaluate t. So x is the value of t, y is the value of u, and you return x divided by y. So if you forget about monads, then with this do notation, this looks like an imperative program. So this is what we can see here. And now the good thing is, if we now want to change the program, and we want to change the program because now we want to do the same change. This was the simple version. Now we want a better version, which also deals with the case that division by 0 should not be allowed. Then basically what we have to change is not the real program. So evil will more or less remain the same. What we change is just the implementation of the monad. So the only thing we change, or almost the only thing that we change, is the implementation of return and bind. But the rest of the program remains the same. And with every new improvement, the same thing happens. The evaluation program remains the same. The definition of return and bind is modified. So What is the advantage? So the advantage is that the main program, namely evil, remains almost the same when performing changes later on. Only the implementation of return and of bind changes. So in this way you have two advantages. One advantage is only few things need to be modified, and moreover you can clearly identify those places where you have to do modifications. You modify the implementations of these monad operations, but you don't modify the big rest of your program. So basically, in reality, these things like the evil program, they would be long and they would change every time. So they would be a long application program. And here, this would be very short because, I mean, you have basically just these two operations, return and bind. And so you know where to change, and changes are very local. So this is the big advantage. So let's see how this would work. So now we do 2 prime. We do evaluation with exception handling, but now with monads. With monads. Okay, so so how did we do it before? Well, we had this data type monad. It was defined like this. So this was the data type maybe, and it looked like value. The only difference was you had this additional data constructor, nothing to depict errors. And now to deal with monads, maybe should also be a monad. So this is the error monad or exception monad. So maybe is the error monad. So what we should do is we should also declare that maybe is also an instance of a monad. And indeed what happened, it is a monad because it again encapsulates a value. A value is encapsulated in these just A objects, but there's another object, nothing, where nothing is encapsulated. So how would we do this? We would say, okay, maybe is also a monad. And now the main change from the old program to the new program is replacing value by maybe. And what's the difference between value and maybe? Well, basically you have another constructor, namely nothing, and you have to change the implementation of return and bind. So what is the implementation of return? What return should do is it should take an object and give you back the encapsulated object. So something, you take an A and you get back an object of type maybe A. So return takes an A and gives you back a maybe A. Okay, and the implementation is basically the same as before. What was called result before is now called just. So just is simply the operator we use for encapsulating. So here there is no big change. Now when we implement bind, there are now two possibilities. Objects are either constructed with just, or the object is nothing. Now if it's constructed with just, so just x, and then a q, it's again defined as before. So if there's an object which is encapsulated by just, we take out this object and apply q to it. So this is as before. Now the only difference in the implementation apart from renaming result to just, is the case where the first argument here is not built with just, but it's nothing. So the only real difference between, there are two real differences in the program, and this is one. One difference is now we have to say what should happen if we combine two maybe objects. The first is nothing, and the second one is something else. Then what should be the result? Now, what should be the result? I mean, we use this to compute things. And if during the computation somewhere you have an error, and nothing means error, then the whole thing should be an error. So whenever you compose maybe objects and there was an error somewhere, then the outcome should also be an error. So this line means, if basically intuitively, if there's an error somewhere in the computation, then the whole computation is erroneous. If there is an error somewhere, then everything is erroneous. Okay, and with this, you can now define evil again. Now, it is interesting to compare this implementation with the one that we had before. So this is evil 1 with monads, and here on the bottom of the slide you have evil 2. Now this is the wrong one. This is without monads. This is with monads. Okay. Now let's first look at this new implementation. Now what does the new implementation do? It is the same as the implementation with maybe that we had before. The only difference is we now use do notation. And we can do this because we said maybe is a monad, and we said how to implement return and bind. Now, this implementation is completely identical to the one that we had before. So if we have a constant x, then we return it. This was the value version. With the maybe version, you have the same thing. If it starts with diff, then before we evaluated t. So x was the value of evaluating t, y was the value of evaluating u, and then we returned x divided by y. So now the beginning is exactly the same. We first evaluate t, then we evaluate u. And now the only difference is, if y is 0, then we have to return nothing, otherwise we return x divided by y. So the difference between this implementation and the implementation up there is this single line. And now, without monads, there were many differences because we always had to make sure that if during the evaluation of t or during the evaluation of u we have an error, then we must make sure that in the end we also have a nothing as a result. Now we don't have to care about this anymore because by this definition of bind, whenever somewhere there's an error, then the whole thing will be an error as well. So this makes sure that an error somewhere over here will lead to an error in the end as well. And now if you compare, you can really see the only difference between the old implementation and this one are two lines, namely this line and the implementation of bind over here. So this is a very, very small difference. And when you do more changes to your program, you can see this effect further and further. So to summarize, what monads do and what's good with monads is, first of all, you make a if you use it for I/O, you can separate side effects from non-side effects. If you use it for programming in general, you can separate certain things, like implementation of return and bind, from other things, namely your real application program, and that leads to modularity, and you only have to do certain small changes when you modify your program. Okay, so next week is no lecture, and then in the week afterwards we continue with the next part of the lecture, and then we look at the theory behind Haskell. So this is the end of the practical part, basically.